A white dwarf, as the remnant left at the end of a star's evolution, although it no longer has nuclear fusion to provide energy, its residual heat is still astonishing, enough to radiate outwards for billions or even tens of billions of years. Since it has enough heat, theoretically it would also have its own habitable zone. If there were planets within this habitable zone, could life also evolve on them? And what kind of experience would life have living on such a planet? We know that white dwarfs are the remnants of low-mass stars. For example, our Sun, in about 5.1 billion years, will also evolve into As a star reaches the end of its evolutionary phase, its nuclear fuel depletes, and nuclear fusion can no longer provide sufficient outward pressure. Consequently, the star's matter collapses inward under its own gravitational force. The star's immense amount of matter and incredibly large mass mean that even the Pauli exclusion principle, the last barrier maintaining the normal structure of matter, cannot withstand the material's collapse, where originally an orbit could only hold 2 electrons. Now, all the outer electrons are squeezed into the same orbit. This is the electron degenerate state that a white dwarf finds itself in. Matter in a degenerate state has an extremely high density. A white dwarf with a mass comparable to the Sun has a volume similar to Earth. Grabbing a handful of white dwarf material would weigh as much as a mountain. Since the progenitor of a white dwarf is, after all, a star's core, its former temperature could reach tens of millions or even hundreds of millions of degrees Celsius. Although its temperature is far lower than before after becoming a white dwarf, its surface temperature can still reach tens of thousands to hundreds of thousands of degrees. In comparison, the Sun's surface is only a mere 6,000 degrees. The amount of stored energy is so vast that a white dwarf can continue to emit light and heat for billions or even tens of billions of years just by relying on its reserves. This is also why we have not yet discovered the existence of a completely cooled white dwarf, also known as a black dwarf. The thermal radiation of white dwarfs is mainly concentrated in the visible and ultraviolet light bands. However, due to their small size, their overall luminosity is not high. Therefore, although white dwarfs can also have habitable zones compared to the Sun, such habitable zones compared to those of white dwarfs are on one hand very close, only a few hundred kilometers away, even closer than the distance from the Moon to the Earth. On the other hand, their scope is very narrow, leaving not much space for planetary orbits. However, they also have an advantage. Given that white dwarfs have a very long lifespan, their habitable zones will last for a very long time. Moreover, compared to the similarly very long-lasting habitable zones of red dwarfs, the habitable zones of white dwarfs are very stable. After all, there is no nuclear fusion inside a white dwarf, which is an unstable factor. It won't occasionally produce solar flares or coronal mass ejections. It merely radiates residual heat like burnt charcoal. In this way, the atmospheres and water of planets around it might be spared. So, does this mean that if there really are planets here, the existence of life on them might not be impossible? Although terrestrial planets can theoretically exist near white dwarfs, planets around white dwarfs are extremely rare. So far, astronomers have only discovered a few, and all of them are gas giants. This is because nearly half of the more than 5,000 confirmed exoplanets were discovered by the Kepler telescope using the transit method. For tiny white dwarfs, the transit method is very unfriendly. Only other methods can be used, such as analyzing the radial velocity method based on the Doppler shift in spectra, or, like recently, directly imaging distant giant planets orbiting small stars using a powerful telescope. Although these methods have not yet discovered terrestrial planets near white dwarfs, some indirect evidence indicates that terrestrial planets indeed once existed around white dwarfs. In 2004, when astronomers observed the white dwarf GD 362, located 150 light-years from Earth, they found that its spectrum was different from other white dwarfs, seeming to contain higher levels of metal elements. This meant that the atmosphere of this white dwarf might have been polluted by external metal elements. 4 years later, astronomers observed through infrared radiation that there was a dust ring around this white dwarf, with a volume equivalent to Saturn's rings. The metal pollution in the white dwarf's atmosphere likely originated from this. Subsequently, through analysis, researchers concluded that this white dwarf, the culprit behind a star's dust ring and atmospheric pollution, might be an asteroid. This is an asteroid, roughly 200 kilometers in diameter, that has been studied. When the white dwarf was still a main sequence star, this asteroid might have originally been part of the crust of a terrestrial planet. Afterwards, that terrestrial planet might have been swallowed and ejected by an expanding red giant, or perhaps torn apart by the tidal forces of the later formed white dwarf. In short, it was disintegrated into fragments. Under the white dwarf's gravitational pull, some of these fragments fell into the white dwarf's atmosphere, leading to metal pollution of the white dwarf's atmosphere, while the remaining parts that hadn't yet fallen in became a dust disk around the white dwarf. Overall, while it is indeed possible for habitable planets to exist around white dwarfs, it is also very difficult for them to remain stable. After all, as a deadly star, its tidal forces are too great and its habitable zone is so close that for a planet to exist stably here, it must meet some stringent conditions. For example, its orbital speed must be very fast, possibly only a few hours, in order to counteract the white dwarf's powerful gravity. In addition, the planet's size cannot be too large, and its density cannot be too low. Otherwise, it would easily be disintegrated by the white dwarf's tidal forces. Therefore, it can be inferred that if you were to visit such a planet first, you might not be able to bear your own weight, because the gravity on it would be very strong. If there were animals on it, they might be small creatures with strong bones and muscles. Here, the sun in the sky, which is the white dwarf, would appear very large, and the radiation would also be very strong. Creatures here might need very strong radiation resistance, or simply hide underground or in deep oceans year-round. However, given its very close proximity to the white dwarf, this planet would most likely be tidally locked, with one side perpetually in daylight and the other perpetually in night. This would inevitably lead to extreme temperature differences on the planet, with life more likely to exist in areas where day and night meet. If such a planet truly exists, perhaps life on it would have an even greater chance to evolve into more advanced civilizations, because compared to planets of main sequence stars, planets of white dwarfs have an abundance of time. Even if today they are still just single-celled organisms, after tens of billions of years of evolution, by the time Earth has long turned to dust, they might just be reaching their prime. All right, this is Lingmo talking about the universe. See you next time. Bye-bye.